Right, good afternoon. Good evening. Y'all here?
Yeah, we can.
All right. All right, nice. Uh, Not much people. All right, so I wouldn't take long today. Today, I just want to introduce something in Module 3. You'll get your handout next week, right? I want to introduce something in Module 3 called the photoelectric effect, right? We just run through it, see how it works something, and just some small calculations probably, and then we will wrap up for today, right? I won't keep all along today. I know some all run all the marathon and thing. Fury, you get any times as yet, or?
Nah, sir, I don't know when I'm releasing that, man.
You have any idea?
I feel
Like,
I take about 20 to 25 minutes.
Okay. I was wondering if small man do under 30 now. You wondering too. All right. How was all you in the cash?
It was good. I think it's in 48 minutes. So
All you
1.5.
was a 7.5, yeah, and all you in
Yeah.
serious and all them hills, and
Yeah, them hills is
kid.
yeah. It's pretty
Yeah,
out.
afraid all you.
Now this is the first time I do that,
Yeah.
and I didn't feel upset afterwards. Like before
Okay, okay.
every time I was with the vomit after that.
All you start by the field and finish by the field.
Yeah, we just start by the entrance by the road. When you
Yeah.
finish, right when you turn the corner to the field, you gotta make a whole rounds on the field, extra 500 meters.
Sure. Okay.
And then it's done.
All right.
Yeah.
All
You should
right.
come next year and try it.
Yeah, well, clash them with naps. I can do that. All right. All right, Ollie. So I don't think anybody else logging in there, right? So let's run through this and have a good idea of what is the photoelectric effect. That's the first thing in module 3, right? We'll do the history and thing behind the photoelectric effect next week when I give you the handout, right? But basically, this experiment kind of changed the way they view matter, right? Because initially they thought, for example, something like light only exhibited wave properties. But this experiment brought about the particle nature, right? And actually, what Einstein was able to show is that every particle has this duality about them. They have both wave and particle. So, for example, a football that we know it to be a particle, it also exhibits wave properties, but at a really, really, really small value that we can't observe. But light, for example, exhibits particle properties, but its wave properties are more prominent. But this experiment showed that it had to have some kind of particle property. Okay, so the basis behind the experiment is that if we take radiation, you all see the little black scribbly lines there. It should work better as your home, right? I don't know if it's lagging, but the black scribbly lines. Let me speed it up. The black scribbly lines hitting a metal, right? So this is a metal. The metal that we are using here is sodium. So this is sodium, and it being hit by radiation. The radiation has this wavelength, right? So the wavelength of that radiation is 300 nanometers. And every time this particular radiation, every time it hits that metal, it knocking electrons out. And these electrons that leave in, those electrons are called photoelectrons. Right? You may not notice that this radiation, right, although it looking like a wave, it kind of clumped up together like a particle. Later on, you will see that Einstein, he called those things photons. I don't know why it's not staying there. Hold on. He later called those particles their photons. So basically, you have photons hitting that metal, right? You have photons hitting that metal, and when that photon hits the metal, electrons leave in. Okay? We'll go through the classical problems and things next week, right? But let's just go with this experiment and see what we observe. So when the photons now hit the metal, electrons will leave the metal. And when the electrons hit the other electrode, what you will notice happening is that if electrons flow in the circuit, right, what you have is current flowing. So you have a current value. And if electrons flowing, then there must be a potential difference, right? And this is the potential difference here. So when the potential difference is 0 volts, the current reading is around here, 0.8 milliamperes. That's the amount of electrons that leave in and flowing in the circuit, right? So that's basically the photoelectric effect. You have radiation hitting a metal, and when it hits the metal, electrons leave the metal, right? That's the concept behind it. But what I want you to notice is this. Let's say I were to raise the intensity. What does intensity mean? Right? I'm gonna slow it down. How it looking for you? It moving fast or it kind of lagging? How the radiation looking?
It lagging a little bit.
It lagging. Okay, I'll leave it at that pace, right? So I'm going to put more radiation. So it might be, I'm going to slow it down even more. So you will see that I'm going to increase the intensity. So you see like one wave coming, and when one wave hit, only one electron leaving, right? So I'm going to increase intensity. So you're going to see now, see that? Now you have more radiation hitting there. And the current value went up. So I increased the intensity and the current value went up. Any idea why? Any idea why the current value went up? Anybody?
Because more electrons making it to the next side.
Right. So more radiation hitting and then more electrons going across. So very good. So you could picture it as you're going in the radiation that's knocking these electrons out, and then the electrons leaving and going to the pole on the next side. All right. Nice. If I increase the intensity further, look at the graph there. You'll see that all that changing is that more electrons going to the next side and the current value going up. All right. So let us leave the value back at about 5, right? I'll leave in the intensity at 5. Right? And I want you to notice something here. I'll leave in the intensity at 5, but I'm going to change the wavelength from 300 nanometers. I'm going to a smaller wavelength. What you notice happening there at that 557 nanometers?
No electrons escaping.
Yeah, no electrons escaping. Right? You all would not have done this as yet. Well, may not have done this as yet, but you see electron volts. Electron volts is equivalent to how much energy the particle has. Electron volts is like when your joule value is really small. When your joule's value real small, it's called electron volts. So what you could do is you could multiply your electron volts by 1.6 by 10 to the minus 19, and you will get your value in joules. All right. So whenever you see electron volts, like you're seeing here, in these two things, whenever you see electron volts, it gives you an idea how much energy. So this is the amount of energy that the radiation or the photons coming in with, right? So that's technically a photon energy. This here, we call it your work function. That is the energy required by an electron to leave sodium, right? So what you'll notice happening there at 557, what you could say about those two energies? What you'll notice? Of course, you're seeing one small than the next, right? So you would recognize, right, correct. You would recognize that the energy for the photons is less than the energy of the sodium, right? Is less than. But what's going to happen here? I'm going to put the energy a little bit more. Let's put it, yeah. Let's give it a little more energy, right? Right. So you'll notice now at 251, you're seeing the electrons. Anybody can say why? Why are you seeing the electrons now? Why are you seeing electrons now when it went to 251? Anybody can guess? Why we seeing the electrons now or photoelectrons now? We weren't seeing it at the lower value. Now at 2.51, we're seeing it. Anybody? Right. So what happening now is that, of course, the photon energy is more. So here's what really happening. What really happening is that the photons hitting the electrons inside the sodium metal and they transfer in the energy. And when they transfer the energy now, that energy goes towards goes to the electron. Now, if that energy is bigger than, in this case is 2.27 electron volts. If it is larger, right? If the energy of the photon is greater than the energy needed for the electrons to leave the sodium, we call that work function. If that is more, then the electrons now have enough energy to break the bonds. And the remaining energy, it will move off with, right? And it will recognize, it going to the next side because it have current flowing, but a real small value. You all okay with that? You all okay with the concept there? Gil, Karina? Gil, listening there, Gil? Shabara, you okay with the concept? So if the energy coming in at the photons is large enough, then the electrons will take that energy, they will break out the bonds, and the remaining, that's what they will leave with. Okay? Because you will recognize here now that if I were to increase this even more, look how much faster the electrons movement, and look how much more going to the next side. Right? So we up the energy, more electrons going. Right? So now if I drop the wavelength and I drop the energy, nothing happening. Nothing happening. So the photoelectric effect appears to be dependent on wavelength and this energy here. Right? So the photoelectric effect is dependent on that. Okay? Shavara, you all okay there?
Yeah, fine.
Okay. So the photoelectric effect is dependent on the photons coming in and the amount of energy, right, they come in with. Okay? You will notice that, for example, right here, even if I increase the intensity, watch this here, I'm going to carry the intensity real high to like 10. That has no effect on the electrons. No electrons going. Right? Because the most important thing, it doesn't have enough. It does not have enough energy. If you can't match the work function of sodium, then it will not happen. Okay? So if you can't match the work function, then nothing will happen, even if you change the intensity. Right? So what we need now is we need to kind of understand those relationships now, right? So let us go back to a higher wavelength that was happening at. Let's put the intensity a little bit lower to about here. Right now, a little bit higher. Let's up the wavelength a little bit more. Right. I want the current value to be around 2. Right. So nice. I still on sodium. I am still on sodium. Now here we're gonna do. We kind of understand what intensity does. Intensity just increases the current or decreases it. We understand that the wavelength increases the energy of the photons, right? And we understand what the work function is. But what about if I wanted to adjust the voltage? Let's say I wanted to make the voltage larger. I go and increase the voltage, right? What's the voltage doing? I increasing the voltage. And when I reach around 3 point, well, I'm gonna be specific, yeah? When I reach around here, right? That current value staying at 3.5, no matter what I do. 3.5, 3.5, 3.5. I can't change the current value. So your graph turns out to look like that. So the voltage now not changing the amount of electrons leaving, right? But watch this here. If I were to drop the voltage now, right, here's 0. Right, that was 0 volts, like right somewhere there. At 0 volts, it went back to 1.8, right? And watch what happening here now. Tell me what you notice happened to the electrons. What happened to the electrons there when the voltage went negative? Hello? Nikash, what happened to the electrons when the voltage started to go negative? Right.
They're staying on the plate, that side plate.
Right, they kind of staying on the plate. But basically what really happening is that they don't have enough energy to go to the next side, right? So like here, around -7, you see less of them going to the next side. And as I go lower and lower, watch what happening. The current value getting lower, smaller and smaller because less electrons go to the next side. And of course, what really happening there, we cannot take the energy away from them. And at a particular value, I'm trying to get it here. Right there. Could I go back up a little bit? At a particular value, minus, hold on, at a particular value, minus 1.3, no current flowing. Watch the circuit. No current flowing there, no current here. So at minus 1.3 volts, I was able to stop the electrons from leaving here and coming here. The electrons still leaving the lattice, but they don't have any energy to reach here. So what I did is I stopped it. So this potential here is what we call the stopping potential. All right, and those are the main concepts that we need to understand in this photoelectric effect. All right, for those who are lost here, let's summarize everything now. Let's summarize this whole process, right? Where, if you wasn't paying attention, pay attention, all right? All right, so here's what Einstein discovered, right? Because there were many things that this experiment could not explain, and Einstein came along and explained it perfectly. Einstein said that the energy, somewhere there, boy. What Zane have it downstairs? What? Right? Sorry. So the energy supplied by the photon, it does two things. It gives the electrons energy to break their bonds. We call that work function. And the remaining energy is its kinetic energy. Right? So that's the summary of the whole thing. If you have to remember the photoelectric effect, if you have to remember one thing from this class view, is this. The energy by the photon goes towards breaking its bond. That's what we call the work function, and the remaining is the kinetic energy. And we have to remember a small relationship now. Energy, this formula was coined by a guy named Max Planck. E is equal to hf. So the energy of a photon is h by f. H is a constant called Planck's constant. I think it have a C in the middle there. It's called Planck constant. Okay? So H is Planck's constant, F is frequency, work function, this is the symbol for work function, and kinetic energy is a half mv squared. Right? Now, this kinetic energy could also be found, I don't know if you all remember this, you should remember this, we just did module 1. Energy is also found by, let me use W. Energy is charged by voltage. So kinetic energy is not just a half mv squared, but is charge of the electron by what we call the stopping potential. So if you know the stopping potential and you multiply it by E, you'll be able to get the kinetic energy. Okay, so that is the summary of photoelectric effect. We have one more thing to look at, right? But the stuff in red, if you can give me a little drawing, all right, that'll be good. Or you can screenshot the page. I don't want to stress you out to make it right and thing, right? All right, so make a note of that. Right, so that is your photoelectric effect, and the part in red is the formulas and the relations to go with it, right? Vedant, you okay with that? So what is EVS? EVS is a next EVS, EV really, right? EV is electron volts, is a next unit for joules. So if you see EVS is a next unit for joules. If you see EVS, E is the charge of an electron, and VS is the thing I was now explaining, called the stopping potential, right? That's the potential that we're seeing right here that makes current 0. So it makes no electrons being able to flow from one point to the next. Okay. To make a note of these things, I'm going to ask some one or two little questions about what you think will happen, right? That graph there, that ammeter versus or current versus voltage graph, is an important graph to learn, right? That shape is a constant shape. And where the dot is blinking, that is your stopping potential. Okay, good. So just some small questions I want you to answer, right? So are removing the stopping potential. Let's put it back at 0 volts. Right? So the electrons happening. I'm going to change the material now. Thing is, I can't pause it. How do I pause it? All right. So here's the question, right? Right. are going to change from sodium. So what's the value here? Know the value here. This question is for, let's start with Amanda. Amanda, this question is for you. Look at the value for the photons coming in. Right? Oh, by the way, write this down. E is equal to HF. That's the one I gave you for energy. And we should remember that the speed of light is F lambda. The speed of light is F lambda. So the formula could also be HC over lambda. So I was trying to show you the connection between wavelength and energy. Actually, before I ask Amanda the question, let us practice that because we never did that before, right? This is the wavelength, and this is the energy value we're supposed to get. So let's see if we could get a value in electron volts. So I will guide you. E is equal to HC on lambda. So I want you to multiply this out for me, right? H is Planck constant, which is 6.63 by 10 to the minus 30. Sorry, I write in too high. .63 by 10 to the minus 34, right? That is the H value. C is the speed of light, so it's 3 by 10 to the 8th. And I want you to divide it by the wavelength. The wavelength is 346 nanometers. So that's 10 to the minus 9. Divide it and tell me what you get for the energy. What you get for the energy. You will not get it 3.58. Eh? I want to show you how to get 3.58. Multiply and divide that F for me. Right, Amanda got 5.75 by 10 to the minus 90. Right, so that is your value in joules. And since it's the first time you're learning to use electron volts, so for some people, I'll show you how to do it, right? So to convert from joules to electron volts, you're going to divide the joules by 1.6 by 10 to the minus 19. So take 5.75 and divide it by 10 to the minus 19. Tell me what you get. I need a little runaway. 3.5. Well, okay, well, close enough. 3.59, right? They probably use the exact value for wavelength, and as I read the wrong class now, they probably use the wrong value for wavelength, and they use the wrong value for, well, they use the exact value for H and thing. All right, but that's the way you convert. That's the way you convert joules to electron volts. Okay. So that's the link. That's the link between wavelength and electron volts. Nice. See if you all could do the reverse, huh? Do the reverse for sodium. Do the reverse for sodium and see if we could find the wavelength that associates with 2.27. Try that fast. See if we could find the wavelength that's associated with 2.27 electron volts. Tell me what you all get, right? Put it in nanometers. Right, so you're just doing the reverse, right? Right, remember lambda will be HC over E. But E must be in joules, right? Tell me how much you got. Right, Nikash got 548 nanometers. Same? Nice. Okay. Later on, you will learn that that wavelength that I just worked out is called a cutoff wavelength. Right? You can't have any wavelength beyond that. That is a cutoff wavelength. Okay, so nice. So you get a little feel of the calculations there. All right, nice. Oh, what did I change up there? Nice. So good. So I want to change the question slightly. Right now we're seeing the photoelectric effect. So my question, Amanda, suppose instead of sodium, by the way, what's your value, right? 3.52 is the photon. Suppose I change it to nickel, 4.48. What do you think will happen? Do you think the photoelectric effect will happen on just put yes or no? If you think it will happen, right? It won't happen, right? No matter changing the intensity, that won't do anything, right? You recognize again, this value is too small. It doesn't have enough energy, right? Good. I want to change one more thing. I want to challenge a little a little more challenging calculation here. Everybody, you have to work on this, right? Let's go back to sodium. I like sodium. Sodium kind of in the, I like change to barium, right? So it happening here. But here's what I want to try to figure out. I want to try to figure out what is the stopping potential. What is the value for stopping potential, right? I want to try to figure out what is the stopping potential value. Everything you see in there is available, right? Remember, E is equal to work function plus EVS. No need to use kinetic energy because we want to get VS, right? So here's my question to you. My question to you is, what will be the VS value? Use everything given there and see if you could work out the VS value, right? Remember, the charge of an electron is 1.6 by 10 to the minus 19. Try that. Tell me what you get for VS. If you get plenty correct answers, yeah, I could even stop because that's what I want you to catch. But I wouldn't stop, what are they saying? Where? Do this one, please. Julie says she go out. Let's see if I get any magic here. If we get any magic here. Good. I'm seeing some values there. Right. So before I convert to joules, I would do this, right? I would say that Vs is the energy of the photon minus the work function over E. Right? So that is 3.52. What's the next one? Right. Minus 2.51. But that value is in, right? That value is in electron volts. So to convert electron volts to joules, I'm multiplying by 1.6 by 10 to the minus 19. So all the maths people now would have recognized this will cancel off here. Right? So your Vs value is 3.52 minus 1.51. And we got 0.1 volts. Right? Very good, Christopher. Anybody else got that? Let's try to observe it now, right? Let's see if we could actually get that on the voltmeter here. All right, so the value going down. Watch it there, going down. Current is now 0.3 milliamperes, 0.9. All right, well, I probably can't get 1.01, but you will see around 1 minus 1 volt here is a stopping potential. All right, so this here is your stopping potential. Anybody confused? Destiny? You're okay there? Shivani, Shavara? All right. You all didn't message answer before, right? Except for Christopher. So I'm gonna give you back one. Let me just change it slightly. All right. That's the stopping potential, and I will just change it to ion. Sorry, and I'll see the value. All right. See if we could get the stopping potential. Okay, now that'll be real hard. Let me try still. Try and get the stopping potential there. It shouldn't take you long at all, yeah? Message answer for your stopping potential, everybody. Oh. Okay, good. Message your values. Let's see if we can get close to it. Yeah, just ask her what you think the stopping potential is. All right, so I only get 3 answers, but yeah, they're looking correct. All right, so it will be the 4.64 minus the 4.36. All right, that will be your stopping potential. All right, how much is that? 0.28, right? That's the value, right? Let's check it out and see. Right, somewhere around minus 0.3, right? Somewhere right, real close to it. See, current is minus. If you look here, you'll see the current value, right? Almost reach 0. One more. Oh gosh, I went too far. Let me go right here, 0. Good, so good. So we know how to calculate that. We understand the concepts of what will allow the photoelectric effect to happen, right? All right, nice. I want to change up something. Okay, so watch this here again, clean up this. Let us continue out this graph, right? What's your graph in black, right? What's the shape of the graph? I'm putting it back at 0 volts. Oh no, I didn't realize the intensity was so high already, right? Okay, anyway, I want to plot the graph. I want to plot the graph an intensity of 5. So this was the intensity at 9 or something. Let's see if we could get the intensity for 5. And I want somebody to tell me what they think the graph will look like. Just make a suggestion of what you think the graph will look like, but the intensity is only 5. So what do you think the current versus voltmeter graph will look like? Anybody could answer. Please, somebody answer. Okay. All right. Thank you, Christopher. So Christopher said that as the I value, as a change in voltage, the current will be smaller. Right? You think the shape would be the same? You all think the shape of the graph would be the same? Nah, the graph would change a little bit because remember, if I drop the intensity to 5, then I should have less current in the circuit, right? So it can't go up as high as this, right? It has to be lower. Okay. What will happen to the shape? Right? Would the shape be the same? What y'all think? Yes or no? The shape will be the same? Right, yeah, the max will be lower. And the same shape and everything. So good. Let's see if that will happen. Right, recognize same stopping potential, because the stopping potential is only dependent on the energy of the photon and the work function. And look at the graph there. Same graph, just lower max current, right? Very good. If I were to lower the intensity even more, watch your graph. Just a little bit lower. Right? If I carry the intensity up to 10, the graph would just be higher. Same shape. Right? Let me just plot out the graph so you can look decent, right? That's it. That's what your graph. So that's a graph that you can learn, right? Right, and you see they all have the same stopping potential. If I were to change the photons coming in, the energy of the photons, by changing the wavelength, then I could change the like right now, can there, like around there, I could change the stopping potential slightly. Right, look at it there. I change it slightly. Okay, so that's the concept of stopping potential. That's the concept of photoelectric effect. And the most important thing for today, for those who want to now tune in and listen, the most important thing is this. Right? The energy supplied by these fellows here, as the photons, is equal to the energy to break the bonds, that's from the metal. And then what they move off with is the remaining kinetic energy. Right? The stopping potential, that's the potential when the current reading is 0. That stopping potential is dependent on this and this. Right? And the stopping potential basically is the voltage that'll make the current here 0, which means that no electrons will leave from one plate to the next. Okay? So that's the concept behind photoelectric effect. Right? So all I want you to gather is that. Right? No calculations, nothing else today. Right? So I hope you all have a little idea of what the photoelectric effect is, right? Even for the ones who are reaching late, right? Where Cheryl gone? Cheryl, you understand the photoelectric effect a little bit? Right? So you can look back at the beginning of the video for those who log in late, right? I'm not going to do any calculations and things. I'm already not replying. Right? When we face-to-face next week, we'll do some calculations. Okay, but that's the concept behind the photoelectric effect. We know about the graph, we know about radiation, we know about work function, and we know about the intensity, right? So just as a quick recap there, make sure you have this, please. Right? Make sure you have the energy of the incoming photon is equal to the work function. That's the energy required by the electrons to break the bonds, and the kinetic energy. Work function is HF. Sorry, energy of the photon is HF. Work function is HF naught. Kinetic energy is a half mv squared. Or we could also say that the energy is hc on lambda, which is equal to hc on lambda naught. These naughts here, I'll tell you what they are. And instead of writing kinetic energy like this, kinetic energy is EVS. All right. And last thing I want you to remember is this is your threshold frequency. That's the smallest frequency for this whole thing to happen. This here is your threshold wavelength, which is the other way around. It's the largest wavelength for this entire thing to happen. Okay, this is your stopping potential. Right, so those are the things that we need to gather from today. And then what do we know? We know the graph of current versus voltage. Right, it's shaped like this is your stopping potential. All right, it's shaped. Hold on, it's shaped like that. don't know how to undo right here. So it's straight here, and then it comes down to your stopping potential, right? I know what they're doing, and we're doing it, trying to screenshot it or highlight or something. Everybody moving around there, or they're just moving. All right. Okay, so that's the summary on the photoelectric effect. That's all I want you to catch for today. Next week, we will go through this and do calculations, and I'll give you a handout. Okay, yeah, I'll do that. All right, so copy it down when you're done, or screenshot or whatever, and keep it. And I'll see you all next week. All right, bye.